Combinations. You should be familiar with the general counting principle and permutations, including the factorial notation to compute answers to permutation questions. In this lesson, we will count the number of ways to choose k objects when we are not concerned with the order of selection. Recall that when we are placing k objects in order, we multiply k terms, beginning with n, and going down by 1 each time. For example, to put 3 colored marbles in order, we multiply the 3 numbers 5 times 4 times 3. But what if we don't care about the order, only the colors chosen? Here's one possible choice: red, black, yellow. These 3 colors make 6 permutations, but it is just one combination of colors. For each combination of 3 colors, there are 3 factorial permutations. In general, for each combination of k objects, there are k factorial ways to rearrange those objects into a permutation. So to get the number of permutations, we can multiply the number of combinations by the number of permutations for each combination. Since we have a formula for counting permutations, we can get a formula for combinations by dividing by k factorial. Similar to permutations, there are several notations for combinations, substituting a c for combination in place of the p for permutation. The final notation is called the binomial coefficient. It places the n and k inside parentheses, stacked as if it were a fraction, except without the fraction bar. It is read n choose k. The reason it is called the binomial coefficient is its connection to Pascal's triangle, which, among other things, determines the coefficients in the expansion of the binomial x plus y to the n power. N choose k is the kth entry in row n of Pascal's triangle, where the nth row begins 1 then n, and the value for k begins at 0 and proceeds to the right, so that when k equals 0, n choose k is 1. When k is 1, n choose k is n, and so on. Here's an example. How many ways are there to select a combination of 3 marbles from a set of 5 when we don't care about the order? To find the answer, we need to find the 5th row, since we are choosing from 5 total marbles. The 5th row begins 1, 5. In the 5th row, we now need to find the entry corresponding to k equals 3. Beginning at the left with k equals 0, we see the numbers 1, 5, 10, 10, 5, 1. These correspond to the k values of 0, 1, 2, 3, 4, and 5. So the entry highlighted in red is the value we need. 5 choose 3 is 10. Here are the 10 combinations. To see that the recursion for Pascal's triangle also makes sense for combinations, we will divide our combinations into 2 categories. The recursion we are looking for is that to find an entry in row n of Pascal's triangle, we look at the previous row, n minus 1, and add the entries that are to the left and to the right in the previous row. Let's use a similar idea to find the number of combinations of 3 marbles drawn from a set of 5 if we know how to find the combinations in a set of 4. We begin by picking a special color and then looking at combinations of the remaining 4 colors. If the 3 marbles contain the blue marble, we need to choose 2 of the remaining 4. So one of the 2 pieces that we need to add together is 4 choose 2. Pick the blue marble and then pick 2 of the remaining 4. The other piece comes from those combinations that don't include blue, in which case we need to choose 3 of the remaining 4, which is 4 choose 3. Altogether, we get 5 choose 3 by adding 4 choose 2 and 4 choose 3. 4 choose 2 is the combinations that include blue, and 4 choose 3 is the combinations that don't include blue.